Hi, my name is Alan Roebuck. I'm the president of the Atmospheric Science section of AGU. I guess that means you can throw shoes at me. I'd like to welcome. One of the great pleasures of my job is I'm going to introduce Jim Hansen to give the Bjerknes lecture. By the way, there's a few seats up in front for those of you standing. You can find seats. Please come up. Jim got his PhD at the University of Iowa and has been a pioneer in climate change research for his whole career, including the effects of volcanic eruptions on climate. And he's a director of the NASA Goddard Institute for Space Studies, member of the National Academy of Sciences, and has many, many other honors. Today he's going to give the named lecture from the Atmospheric Sciences section, named after Jacob Bjerknes. And the title is, well, before that, I want to give him a certificate. So.
Sir, you need to make a seat because I'll let him know.
What does that mean?
I'll tell you.
So, if you could stand. This is just a certificate, so.
Look this way.
Okay, thanks very much. I changed the title of my talk from what I gave a few months ago. Global warming has implications for energy policy and intergenerational justice. The propriety of the scientists discussing these implications is self-evident. Now, I will argue that we have a much sharper knowledge of global climate sensitivity than is usually stated. And the Faustian bargain that we have cut for ourselves is nastier than has been recognized. And I want to emphasize some important missing observations. The urgency of the implications for energy policy is not yet adequately recognized by governments, but it must be. The implication for intergenerational equity, I think, also deserves greater attention. How do I switch these?
The left mouse button.
The left mouse button. Oops.
The right one is to go back.
Okay. 2008 will probably be the 9th warmest year in the period of instrumental data. Since 1998, which was anomalously warm due to the El Nino of the century, only 1999 and 2000 were cooler than 2008. However, as I will show, the 2008 temperature is a fluctuation. It does not indicate a change in the long-term warming trend. These maps compare the temperature anomalies of 2008 and the first 7 years of this century. The map on the left shows the temperature anomaly of the past 12 months relative to the base period 1951 to 1980. It is unusually warm in most of Eurasia, the Arctic, and the Antarctic Peninsula. The Pacific Ocean is notably cool in 2008, as there was a strong La Nina early in the year. But except for the Americas, the rest of the world was not cool compared to prior years. Now, the global temperature at seasonal resolution is shown by the top curve. The greater variability of the low latitude temperature, the second curve, is associated with the southern oscillation, as shown by the red-blue curve at the bottom, which is the Nino 3-4 index for the southern oscillation. Low latitude and global temperatures have largely recovered from the cool conditions of early 2008, which were associated with a moderately strong La Nina. Now, the effect of the southern oscillation on global temperatures is easier to see if we get rid of the noisy land data. This is the monthly global ocean surface temperature. The El Nino of the century in 1997, 1998 is obvious, as is the recent La Nina. This La Nina is the main reason for the relative coolness of early 2008. Now, let me make note of one assertion that the world could be headed into colder times because of changes on the sun, because that misconception has been spread widely. Solar irradiance has been measured since the late 1970s, and the solar irradiance remains at or near a prolonged solar minimum, which is deeper than, apparently deeper than the prior measured minima. This is data of Froelich and Lean through the end of September. These solar irradiance variations do not have any known relation with short period oscillations of Pacific Ocean temperature. In a few moments, I will show quantitatively that the effect of the sun is not negligible, but it is much smaller than the climate forcing due to human-made greenhouse gases. Our understanding of climate change comes principally from the history of the Earth, from increasingly detailed knowledge of how the Earth responded in the past to changes of boundary conditions, including atmospheric composition. And our second most important source of understanding comes from global observation of what is happening now in response to perturbations of the past century, especially the rapid warming of the past 3 decades. Climate models used with understanding of their limitations are useful, especially for extrapolating into the future, but they are clearly number 3 on this list. Deterministic global temperature change depends mainly upon 3 things. The equilibrium climate sensitivity, the forcings that are applied to the system, and the response time, which is primarily determined by the ocean. Recent research and data clarify the status of our understanding of these 3 characteristics with important implications. If all 3 of these were unknown, we would have a very difficult time understanding climate change and making predictions. Fortunately, if we are clever enough in how we define climate sensitivity, we can now specify it with great precision and accuracy. We have good records of the long-lived atmospheric gases from ice cores covering 400,000 and even 800,000 years. And records of the temperature, not only from the ice cores, but from ocean cores all around the world ocean. We can compare the last ice age, 20,000 years ago, with the current interglacial period, considering the surface conditions and the long-lived greenhouse gases as specified boundary conditions. This yields an empirical climate sensitivity. It is 3/4 of a degree per watt per meter squared, or 3 degrees for doubled CO2. This climate sensitivity includes all fast feedback processes: water vapor, clouds, sea ice, snow, and aerosols. The physics is exact. It is not modeled. All of the feedbacks operate correctly. It is important to realize that aerosols should be included as a fast feedback. As the planet becomes warmer, the atmosphere is moister and the aerosols load is reduced. This is consistent with recent satellite observations, which show a decreasing background aerosol amount as the planet has become warmer, even though the global aerosol source strength did not decrease. We know sea level for the full 400,000 years, which implies the ice sheet size and the surface albedo. We also know the greenhouse gas amounts versus time. These two forcings multiplied by 3/4 of a degree per watt yield good agreement with observed temperature for the entire record. Now we can look at 800,000 years. The same sensitivity fits for the earlier times even better. The bottom line is that the fast feedback climate sensitivity is really nailed. It is 3 degrees for doubled CO2 plus or minus half a degree. I'm going the wrong way. Now note, it is unwise to attempt to treat glacial, interglacial aerosol changes as a specified boundary condition, as I did in 1984, because aerosols are inhomogeneously distributed. Their forcing depends strongly on the aerosol altitude and the aerosol absorptivity, all of which are poorly known. But why even attempt that? Because human-made aerosol changes are a forcing, but aerosol changes in response to climate change are fast feedback. Second, the accuracy of our knowledge of climate sensitivity is set by our best source of information, not by bad sources. Estimates of climate sensitivity based on the last 100 years of climate change are practically worthless because we do not know how the net climate forcing changed. So the equilibrium climate sensitivity is well known, but that still leaves two uncertainties, the climate forcings and the climate response time. Everybody understands that the forcings are uncertain. There are two major forcings in the industrial era, both human-made. The greenhouse gas forcing is large and positive, causing warming, and it is known very accurately. The aerosols cause a net negative forcing via their direct effect on sunlight and their effect on cloud properties. But the error bars are huge. IPCC has a good way of showing this uncertainty. The greenhouse gas forcing is a sharp function well known at about +3 watts. But the aerosol forcing might be anywhere between 0 and -3 watts. So the net forcing, the red area, is anywhere between 0 and +3 watts, probably between +1 and +2 watts per meter squared. How do the different climate modeling groups decide upon the aerosol forcing? Well, I asked my granddaughter Sophie, and she said that it was about 2 watts. Her brother could only count 1 watt. But I took Sophie's advice, not Connor's. Now, I'm just kidding, of course, but we had a rationale for the aerosol forcing that we used. But my point is that there is a good deal of arbitrariness in the decision. And we must admit that the error bar is huge. So keep in mind that it is almost as likely that the actual net forcing is closer to Connor's 1 watt as to Sophie's 2 watts. And why is this important? 1 watt or 2 watts? Partly because of the Faustian bargain that humanity has made. If Sophie is right, the aerosols have only reduced the greenhouse gas forcing from 3 to 2 watts. But if Connor is right, the climate change we have already seen is a consequence of only about 1 watt net forcing, implying that most of the greenhouse warming is still hidden by aerosols. In that event, just as Dr. Faustus, after enjoying the fruits of his dreams, was eventually dragged off to Hades with fearful shrieking, so too humanity, after enjoying the economic fruits of fossil fuels, may be dragged to its doom. Unfortunately, the people suffering from such a fate may be Sophie and Connor and all of their cohorts rather than the parties that made the bargain, but that's a later part of my talk. Back to this 1 watt, 2 watts. Unfortunately, new information suggests that the truth is somewhere to the left of Sophie. But how close it is to Connor's 1 watt is unclear. When we use Sophie's 2 watts net forcing, we get beautiful agreement with observed global temperature over the past century. And this climate model, the GISS climate model, has sensitivity 3 degrees Celsius for doubled CO2, which is realistic. So does this result confirm that the net climate forcing really is about 2 watts? No, because there is another important variable, the climate response time. And we now have several reasons to believe that the climate response time of the GISS ocean model and most ocean models is probably too long. Most of the IPCC ocean models seem to mix too rapidly. This is the climate response function for the GISS model with the Russell Ocean. The response function is the fraction of the equilibrium response to an instantaneous forcing, in this case an instant doubling of atmospheric CO2. Only 60% is achieved after a century and 90% after a millennium. IPCC did not ask modelers to supply their climate response function, which is the most important characterization of the ocean model. But fortunately, Tom Delworth at GFDL and Gurkan Dena Basaglu at NCAR and Jonathan Gregory of the UK for the Hadley model all provided me data a few days ago for long runs of their models. And the comparisons show that all 4 of these models have similarly long surface temperature response times. Unfortunately, this does not indicate that the models are right. On the contrary, there are numerous indications that they have a common problem. First, overall, they tend to mix transient tracers more than observed. Second, theoretical work at GISS by Vittorio Canuto's group shows that the mixing parameterization, such as the common KPP approximation, cause too much mixing in the upper ocean. And third, there is the most important measurement, and that's the change of ocean heat content. 20 years ago, when I was asked what's the most important measurement for global climate change, I said ocean heat storage because that defines the planet's energy imbalance. The measurements are getting better, but they are mainly in the upper ocean. And reanalyses of old data, such as this one for the upper 700 meters, are doing a better job of correcting for instrumental changes, but there are still big uncertainties and there's disagreements between researchers. The situation in the deep ocean is worse. There is not enough good data. This Levitas analysis yields very little heat gain in the deep ocean. I think that he may underestimate heat storage because of an assumption of no change where no observations exist. Nevertheless, the ocean data show very little increase of ocean heat in the past several years. Overall, it has become clear that there is a discrepancy between observations and the heat gain that is calculated in most models if the models use a net human-made forcing of +2 watts and if the oceans mix as deeply as most ocean models do. Most of the IPCC models have had a realistic sensitivity of most of the models that did have a realistic sensitivity of 3 degrees for double CO2 used a net forcing of about 2 watts. Now, conceivably, there is a subconscious preference for a forcing that yields a surface warming similar to that observed. Now, if the climate model response function is too slow, the surface response function, then what does that imply? It means that the net forcing must be less than 2 watts if we want to retain close agreement with observed global warming. Can we say something quantitatively without waiting for the next generation of ocean models? Well, maybe, because this climate response function is the simple Green's function for the climate model. All we have to do is multiply the response function by the annual change of forcing and integrate over time. So in 10 to the minus 7 seconds, we obtain a predicted global temperature change, and the result, the red curve, agrees very well with the GCM result, which required 10 to the plus 7 seconds, or 4 months. So we save a factor of 10 to the 14th in computing time. Now, the bumps and valleys in the response function are chaos. So if we want to see the effect of forcings clearly, it may be better to take a linear fit to the response function, shown by the blue line. Using the linearly smooth response function, we lose the realistic-looking interannual variability, but we can see the calculated response to forcings such as volcanoes more easily. Now, the real world probably falls between the blue line and the red curves, the blue and red curves, but we know not where. The faster climate response function, the red curve, would require a net forcing closer to Connor's 1 watt. Are there any testable consequences of these two alternatives? Well, if Connor is right, if the net forcing is closer to 1 watt, then the portion of the forcing that the planet has not yet responded to is much smaller than in the case of the 2 watt forcing. The planet is closer to energy balance. That means that global temperature will be more responsive to ongoing changes of global climate forcings, even moderate changes such as the solar irradiance changes of a couple tenths of a watt. An example is shown in this calculation using the fast response function and increasing the aerosol forcing so that the net forcing is only 1.3 watts rather than 2 watts. This smaller net forcing makes the effect of the solar cycle, however, only a bit more apparent in the waviness of the computed temperature, which rises to a new record within the next few years. The calculation assumes that the coming solar cycle will be similar to the last one. So I expect to see new global temperature records within several years as the solar cycle increases. But when you add in chaotic variability, short-term change of global temperature does not provide a very strong discriminant for the forcing. So I went back to Sophie and Connor 3 years later, and I asked them again, what is it, 1 watt or 2 watts? And they said they didn't know. Now, the instrument that can measure stratospheric aerosol properties with, I think I skipped something here, but I wanted to make a point that some of the key measurements are not being made. And one example is stratospheric aerosols. I did get some estimates from Larry Thomason for some recent small volcanoes, but the estimates are only good within 50% or so because we're not measuring them anymore. The SAGE 3 instrument is sitting on a shelf at Langley Research Center. There are now plans to measure tropospheric aerosols with the needed accuracy for the first time with the Glory mission in 2009, but there's no follow-on measurements on the books. When the NASA administrator and the White House eliminated the first line of the NASA mission statement to understand and protect the home planet, and they slashed the Earth science budget, there are consequences to that. And climate change is a research problem. It requires decadal measurements, and it is not a problem that can be handed over to an operational agency. Now, back to paleoclimate. It is useful to look at longer time scales. Pleistocene climate oscillations are complex, including dynamics and interactions. But the detailed information that we have on Pleistocene oscillations should not cause us to lose sight of the forest for the trees. The surface albedo change, for example, in going from ice-free state, such as existed 50 million years ago, to the depths of the ice age or even to snowball Earth conditions, is entirely a feedback which makes climate more sensitive. Between the depths of the last ice age and deglaciation of Antarctica, climate sensitivity to a specified greenhouse gas change is doubled to about 6 degrees Celsius for double CO2 because of the surface albedo feedback. Now, the dominant climate forcing over at least the first half of the Cenozoic must have been CO2, because CO2 was as much as 1,000 ppm, causing a forcing of more than 10 watts per meter squared relative to glacial periods. Other candidate forcings are an order of magnitude smaller. The large CO2 changes are no surprise, as volcanic source and the weathering sink of CO2 are not in general balanced. At the beginning of the Cenozoic, when India was still south of the equator, moving north rapidly at 20 centimeters per year, plowing through the Tethys Ocean that had long been the depot center for carbonate sediments from major rivers of the world. The subduction and metamorphosis of the ocean crust with resulting volcanic emissions of CO2 caused the planet to warm until India collided with Asia about 50 million years ago. Then, as the source of CO2 decreased and the sink due to weathering of the Himalayas and Tibetan Plateau increased, the planet cooled until we estimate in a recent paper that CO2, when it had decreased to about 450 ppm, and at that point Antarctica glaciated quite rapidly. Now, two conclusions should be emphasized. First, the natural imbalance between geologic sources and sinks of CO2 is of the order of 10 to the minus 4 ppm per year. So in a million years, that can cause a change of 100 ppm. But the human-made rate of change is today about 2 ppm per year, which is 10,000 times greater than the natural rate. So the assertion that we should not be too concerned about human-made climate change because there have been much greater natural climate changes is nonsensical, because there have been larger changes, but on very long time scales. On any time scale of interest to humanity, humans are now in charge of the climate change. The second conclusion is that we cannot burn all of the fossil fuels, which would more than double the amount of CO2 in the air. We can't do that without setting the planet on a course to the ice-free state. It would be a rocky trip, and it would take some time as the ice sheets collapsed and sea level rose 250 feet. But feedbacks work in both directions. Ice sheet formation is reversible. Now, the Venus syndrome is the greatest threat to the planet, to humanity's continued existence. Earth is Goldilocks' choice among the planets, the one that is just right for life to exist, not too hot and not too cold. Now, how does the Earth manage to stay in this habitable range? Is there a Gaia phenomenon? It keeps the climate in bounds. It's a nice idea, but it doesn't work. The Earth's climate becomes more sensitive as it becomes very cold. When an amplifying feedback, the surface albedo, can cause a runaway snowball Earth with ice and snow forming all the way to the equator. If the planet gets too warm, the water vapor feedback can cause a runaway greenhouse effect. The ocean boils into the atmosphere and life is extinguished. The Earth has fell off the wagon several times in the cold direction, ice and snow reaching all the way to the equator. Earth can escape from snowball conditions because weathering slows down and CO2 accumulates in the air until there is enough to melt the ice and snow, which will then rapidly melt as the feedbacks work in the opposite direction. The last snowball Earth occurred about 680 million years ago. Now, the danger that we face is the Venus syndrome. There is no escape from the Venus syndrome. Venus will never have oceans again. Given the solar constant that we have today, how large a forcing must be maintained to cause runaway global warming? Well, our model blows up before the oceans boil, but it suggests that perhaps runaway conditions could occur with added forcing as small as 10 to 20 watts per meter squared. I go the wrong way. Yeah. There have been times in the Earth's history when CO2 was probably about as high as 4,000 ppm without causing a runaway greenhouse effect, but the solar irradiance was less at that time. What is different about the human-made forcing is the rapidity at which we are increasing it on the time scale of a century or a few centuries. It does not provide enough time for feedback such as changes in the weathering rate to come into play significantly. There is a danger that humans could cause the release of methane hydrates, perhaps more rapidly than occurred in some of the cases in the geologic record. In my opinion, if we burn all of the coal, there's a good chance that we will initiate the runaway greenhouse effect. And I think if we also burn the tar sands and the tar shale, then I think it's a dead certainty that we would do that. Now, that would be the ultimate Faustian bargain. Mephistopheles would carry off, unfortunately, not only the shrieking robber barons, but unfortunately and permanently all of the life on the planet. Now, all of the countries in the world have agreed that we should stabilize greenhouse gases at a level that avoids dangerous human interference, but what is dangerous has not been defined. I think that extermination of species and ice sheet disintegration should be at the top of the list of what determines dangerous, because those are both irreversible on any time scale that humanity can think about. And there is the danger of passing tipping points. We probably already have the CO2 past the tipping level that will cause some tipping effects, such as loss of Arctic sea ice. But we haven't passed, I think, the point of no return for the important tipping points such as the stability of the ice sheets and retention of most of the species on the planet. The one where we probably have passed the tipping level is the Arctic sea ice, which has decreased to just over half. The summer minimum at the end of the summer is not much more than half of what it was a few decades ago, even though it's a little bit more this year than it was last year, and perhaps slightly affected by the small volcanoes, which have caused the recent sunsets and reduced the sunlight a little bit at the high latitudes. But if we wanted to stop the Arctic sea ice from decreasing, we would need to restore the planet's energy balance. And that probably means reducing CO2 to no more than 350 parts per million. As for the ice sheets, the area with summer melt fluctuates from year to year due to the weather fluctuations, but the area has been increasing. And in 2007, it had the largest area in the period of satellite data. And that meltwater, in general, doesn't make it to the edge of the ice sheet. It will burrow a hole in the ice sheet and go to the base of the ice sheet, and there it will speed up the discharge of giant icebergs to the ocean, and also the loss of ice shelves has a similar effect. And we know that the increased melting is winning out over the increased snowfall in the winter because the ice sheets are losing mass, as shown by the measurements of the gravitational field by the GRACE satellite, which shows that the ice sheets get heavier in the winter, but they lose more mass in the melting season, and Greenland is now losing mass at a rate of about 200 cubic kilometers per year. And that's a significant change over the last 15 or 20 years. It probably was close to mass balance a couple of decades ago. If we wanted sea level to be stable, clearly CO2 would have to be less than its present amount, because West Antarctica, as well as Greenland, is beginning to lose mass at a significant rate. The paleoclimate data suggests that if you want ice sheets comparable in size to the current ones, you probably should have CO2 not greater than about 300 ppm. Another effect that gives us a criteria is the expansion of the subtropics. The overturning Hadley circulation cell is expected to expand as global warming increases, and empirically it is observed to have increased on the average by about 4 degrees of latitude, and that's part of the reason that Lake Powell and Lake Mead are only half full. And this expansion of the subtropics is already affecting the Mediterranean region and the southern United States and Australia, parts of Africa. The frequency and area of fires in the West has increased by about a factor of 4. One of the biggest effects is the melting of alpine glaciers, which supply fresh water to hundreds of millions of people, the rivers that originate in the Himalayas and in the Rockies and in the Andes Mountains. Once these glaciers are gone, you'll still get the big flush of fresh water in the spring as the snow melts, but the continued melt during the summer and fall that provides much of the water for the rivers will not be there. And at the rate they're going, almost all the glaciers will be gone within 50 years if we stay on business as usual. The coral reefs are another criteria. They're under stress for a number of reasons, but 2 of the important reasons are the acidification of the ocean, which affects the shells and the skeletons of life that has carbonate skeletons, and the temperature increase is also a source of stress for the coral reefs. And these are the site for about almost 1/3 of the species in the ocean. So all of these criteria suggest that it would make a lot of sense to aim for a target atmospheric CO2 of no more than 350 parts per million, and probably less than that. But already if you aim at 350, it means you've got to get on a completely different path than what we're doing. And we can refine the target later if we start getting onto a reasonable path. If we want to preserve the planet on which civilization developed, we had better get on a very different carbon dioxide path. And the problem is that, and the reason that CO2 has to be the focus, even though there are other climate forcings that are important, is because of its lifetime. You know, when you put a pulse of CO2 in the atmosphere by burning fossil fuels, it begins to disappear quite rapidly, and after just about 25 years, about half of it is gone, mostly into the ocean. But then the ocean begins to resist taking up any more of it because the CO2 can come back out, and until the CO2 that's been taken up by the ocean is deposited on the ocean floor as carbonates, it's not going to take up all of the CO2. Even after 1,000 years, of the order of a fifth of it is left in the atmosphere. So that means that we cannot burn all of the fossil fuels. The purple portions of those bars are the part of oil, gas, and coal that has already been burned and put in the atmosphere. And we're probably going to put most of the oil into the atmosphere, and it's not practical to capture CO2 coming out of a tailpipe. But what is most important is the coal, because it's the biggest potential source, and it's the one that we could decide either to leave it in the ground or to use it at power plants, only at power plants where you capture the CO2 and put it back in the ground. If you did that, then the CO2 would peak at something between 400 and 425 ppm, depending upon whose estimates are more accurate for the undiscovered reserves of oil and gas. And it would then be feasible to get back below 350 ppm by means of steps such as improved forestry and agricultural practices. So it's technically feasible to get back to 350 ppm, but the critical thing is you would have to phase out coal emissions. I should say that in that last curve, that last graph, I assumed that coal was phased out. Coal emissions are phased out between 2010 and 2030, and that's a tall order, but it's technically possible. So although fossil fuel companies and governments, energy departments, think it's a God-given fact that we're going to burn all the fossil fuels, in fact, we can't do that. And we should have a free will alternative, and it requires a number of things, but by far the most important of them are phasing out the coal emissions, and we're going to have to figure out how to power our society with energy sources other than fossil fuels anyhow, so why not do it sooner rather than later? And I think that the two essential things are, first of all, the coal emissions phase out, which I've mentioned, and also you're going to have to put a price on carbon emissions, or the goals and the caps are just not going to work. And I think in order for people to accept a carbon tax, you're going to have to give the money back to the public on a per capita basis, so that the person who does better than average in reducing his emissions will actually make money. Then I think we could get a carbon price that's high enough to do the job, and we could phase out carbon emissions. That's some details about that suggestion. But this is my newest grandchild, my son's first child. And Jake has not done much of anything to cause global warming. He can't even walk yet. He crawls pretty fast, and I interrupted him crawling across the floor when I took this photo. He looked up at me as he was crawling. But he will feel, my parents lived to more than about 90 years old, so Jake will probably be around toward the end of the century. So he and his cohorts will feel the full effect, even though they haven't done much to cause it. That's what I call the intergenerational inequity. And in the case of our parents, they had a legitimate defense because they did not know the problem that they were causing. But that defense is no longer viable. And I think that continued failure of the political process is going to cause, and it should cause, increasing public protests, because there's just what's actually, though there are a lot of governments who say they understand this problem, in fact, it's almost entirely greenwash. The actual actions consist of goals, and even our best friends and the most serious are not doing anything close to what is needed. For example, Japan is took the strongest goals for its reductions in Kyoto Protocol. But if you look at the Japanese emissions, they actually increased significantly. Well, they bought a clean development mechanism, rights to pollute, and that was supposed to reduce China's emissions, but they went up exponentially. And it's similar in other countries that are, as I say, they're the ones that appear to be the most serious, but the actions don't correspond. So that's, and there are some cases where this was a case of King's North in the United Kingdom, and the jury of peers in Kent, England, found the people who had caused this $65,000 worth of damage by blocking the operations at a coal-fired power plant. They found them innocent, but still that doesn't solve the problem. And I think even in the, I guess I've used my time, but this is a issue which, although it's now getting a lot of publicity, we haven't yet figured out how to deal with it. And I think we've got to get politicians to understand that it's more serious and we're at a more critical stage than they seem to understand. Thanks.
Thanks very much, Jim. You'll take some questions?
Sure.
Kurt, please repeat the question.
Fast to make definite predictions, just to get people thinking. And you did say that you thought that we will exceed 1998 global mean temperatures fairly soon. Would you care to be more specific?
Yeah, the question was, am I willing to make a prediction about, I'd said that because, and the reason I think I can make a prediction with some confidence is that the realization that the planet is a little closer to energy balance than I would have said 3 years ago. And that means that things like the solar cycle have a little bit more impact. And that's why on this calculation I was showing, there was fairly strong warming over the next 5 years. So I think that I would say that during Barack Obama's first term, we're going to see warm enough temperatures exceeding the prior records that it will help get people's attention. But I hope we don't have to wait for that in order for the new administration to take some stronger position and actions. But so that would be my prediction. Within his first term, we will see higher global temperatures, which all the groups who analyze temperature will agree that it's significantly exceeded any previous year. But you know, if another Pinatubo occurred next month, that might have an effect, but that's very unlikely.
Jim, remember K.J. Tung's work on the temperature response to the solar cycle? Because from a very different direction, he's reached a conclusion about sensitivity and response times, I think very similar to yours.
I don't know. There are, I think, a few attempts to extract a solar cycle signal from data, and they are fairly convincing that it is there, and that is, as you say, is consistent with what I'm saying. So the question about solar is really whether there are any longer period other than these 11-year up and downs of 1/10 to 2/10 of a watt. And that's very interesting because we have been stuck in this solar minimum for quite a bit longer than the previous solar minima, but it does look like we're probably about to come out of that. But you know, we still haven't really figured out whether the Maunder minimum really was significantly less solar irradiance, and if it was, there's nothing to prevent that from happening again. But I'm expecting the solar cycle to now begin to pick up. We will find out soon enough, I think, within the next several months.
Jim, I fully support your message. However, I have some questions concerning the science. In the transition from last ice age to Holocene, you have classified dust as a fast feedback rather than the forcing. However, dust starts decreasing about 2,000 years before temperatures start rising and CO2 goes up. So my question is, how dust can be 2,000 years before what is apparently causing this? So my suggestion is not really dust the first forcing which comes?
Well, so the question is, should dust 12,000 years ago be counted as a forcing or a feedback? Well, if it's a forcing, who caused it? There weren't enough people around to do that. It's the changes in dust are related to changes in climate. We see when it's drier, you get dust into the air more easily, and there are hypotheses about how dimethyl sulfide is related to changes in the ocean's temperature and climate. Those are feedbacks. Those are climate-related changes. There weren't any. So I think it's appropriate to count the natural aerosol changes as fast feedback.
The genie is out of the bottle in a sense, and geoengineering has been on the table now for several years, actually, like more than several. What do you think about geoengineering solutions? What do you think the prospects are for geoengineering in the coming century?
Yeah, the question is about the question is, what about geoengineering? What are the prospects for that? Because it is now beginning to be talked about seriously. Well, of course, the whole experiment is geoengineering, the whole CO2 change. And I think that I would call things like improved agricultural practices that attempt to store more carbon in the soil, whether by biochar techniques or minimal till agriculture and things. Those are geoengineering of a sort, and even reforestation. You're trying to draw CO2 out of the atmosphere. I think those are the kind of places you should start. You could even consider burning biofuels at a power plant where you capture the CO2 and sequester it. I don't think there really is any such thing as clean coal, but nevertheless I think we should work on carbon capture and storage because it may be useful for things like burning biofuels and capturing the CO2, and that way drawing down the amount of CO2 in the atmosphere. I mean, as a last resort, if you saw that the Venus syndrome was coming upon us, then obviously you lose your resistance to geoengineering, and you might do some drastic things. Or even if the ice sheets were starting to collapse, who wants to have a 25-meter rise of sea level? So you might then be more likely to do more extreme geoengineering things. But I would say it's the soft ones that you should be serious about early on.
Yes.
You put a rather short time scale before catastrophe would happen. I believe you. And I would argue, I don't think there's anything we can do in this time scale, with China now emitting more CO2 than New York, with India not yet heard of. You mentioned the possibility of burning biofuels. We can't produce enough biofuels to be significant. Is the planet really just doomed?
Well, the question is it too late? You know, I didn't show the curve for the climate forcings. It's actually, although you keep reading these things that, oh, things are going faster than IPCC said they would do, that's not really true. If you count up the forcings, it's actually slowed down a bit because chlorofluorocarbons, instead of increasing, are actually now slowly decreasing. And methane, except for last year where it started to increase again, its rate is slower. So if you look at the period 1970 to 2000, it's the last decade. So I think that China and India would love to have other sources of energy than coal. Now, this gets me in trouble with a lot of environmentalists, but I think we should not have stopped our research, R&D, on fourth-generation nuclear power, because fourth-generation nuclear power is a sort where you could burn nuclear waste. Right now, with the light water reactors, more than 99% of the energy is ending up in a waste pile, which has a half-life of 10 to hundreds of thousands of years, while you could burn that and get the other 99% of the energy and end up with stuff that has a half-life of a couple of decades. And if you did that, you would not need to go mine uranium for about 1,000 years, because we've got enough nuclear waste and weapons-grade material that could be burned to provide the energy for hundreds of years. And that's the kind of thing where India, which doesn't have much other possibilities, could. So if we would, so I think that kind of thing should be looked at least, because it's great if Al Gore is right that we can get all of our energy from renewable energies with a better electric grid and energy efficiency. That's fine, but I don't think we should bank on that. At the same time, we should be doing the R&D on both next-generation nuclear power and carbon capture and sequestration. Because even if we don't want to use coal, the CCS might be useful. But so I think we will solve the problem, but it does probably require a carbon price, which is significant and which is rising, because then you're going to bring innovation into the system where entrepreneurs will want to make a lot of money and find carbon-free energy sources and energy efficiency and things which people will buy. And if you have 100% dividend on that carbon tax, people will have money in their pocket to buy these new products. So I think if we would just tell the truth, and it does require a carbon price, and politicians are not willing to do that. But maybe when they understand how serious it is, they will take that step.
Okay, we'll have one more question.
Very big if, but if China were to stop burning dirty coal, what are the implications for changes in radiation forcing, particularly with the two estimates from your grandchildren?
Yeah. The question is, what if people do stop burning coal? What about the uncovering the warming that the aerosols have been shielding? Well, we need to understand that better. That's why I say we need to have measurements to make sure we understand that. But that tells us, for one thing, we should be emphasizing in our efforts to clean up the air, we should focus more on the black aerosols because those are ones that actually cause warming. So if we have a greater emphasis on the soot, the black soot, then and we're probably never going to clean out all of the human-made aerosols, and it is nonlinear, where the first aerosols in a pristine atmosphere have more effect on clouds than later ones. So we may always have some negative forcing from the aerosols, but it's a good question.
Okay, thanks again, Jim.